Hi, 7th grade. This video goes with lesson 12.7, Theoretical and Experimental Probability. There are quite a few definitions in this lesson. However, they were all taught last year in our probability chapter of pre-algebra, so it should all be very familiar to you. The notations should all look very familiar. There's one definition we might not have included last year that we are going to cover. I just can't quite remember if we did that one last year or not. So when we get to it, I'll point it out. Otherwise, this should go pretty smoothly, I'm hoping. So to start with some definitions, we have outcomes, which are the possible results of a single trial, such as flipping a coin or spinning a wheel. So you have all types of outcomes depending on an event, which we'll get to here in a moment. Sample space, your sample space consists of all the possible outcomes, and it is going to be written in set notation, as you can see down here. Those are your curly brackets or your braces. The event is any outcome or group of outcomes for a specified goal or characteristic. And then your favorable outcomes are the outcomes that match that given event. So they all work together. So here we have the event that if we roll a standard number cube or a die, the event is that we roll an even. Our sample space includes all of the outcomes or possible results of rolling a number cube once. Those outcomes would be 1, 2, 3, 4, 5, and 6. The favorable outcomes are the outcomes within the sample space that satisfy the event, so 2, 4, and 6. So all these definitions work together to create what we know as probability. So probability of an event tells how likely it is that that event will occur. A notation that we used last year, and I was pretty picky about this, was a capital P and then the event description inside parentheses here. It could be one word, it could be a sentence, as long as it's detailed enough so that you are clear, or the person reading your notation is clear on what you're looking for as far as probability is concerned. Probability can be written as a fraction, decimal, or percent. Fractions are the best. That way you don't have to round anything. Percents are often spoken a lot more commonly just because they sound better. And then as far as the decimal, that's more higher math level. You'll use decimals more often. So it's completely up to you. I tend to write my probabilities as fractions or percents. And last year, you did not lose points if you did not simplify your fractions, just for the probability chapter. However, we want to go away from that. We want to continue to simplify all of our fractions. So if you have a probability of 4 out of 8, you should say the probability is 1/2 or 50%. Okay? And the last piece here, the probability of an event ranges from 0 to 1 or 0% to 100%. And here we have a scale, which I believe I probably drew for you last year. If not, here it is. You go from 0 or 0%, which means the probability is impossible, to 1 or 100%, which means the probability is certain. Halfway through, that means the probability is as equally likely of one or over the other from happening, or 50%. And the closer to 0 you get, the less likely, the higher or closer you get to 100% would be more likely. And here's the notation. The probability of your event equals the number of favorable outcomes out of the total number of outcomes. So let's take a look at, wrong page. Let's take a look here. Oh, we got another definition. Theoretical probability. We're going to be looking at theoretical versus experimental. The idea is still the same, but how you get to the probabilities is technically different. So theoretical probability is the theory behind probability, or what is expected to happen after one trial. So the probability of rolling an even on a die, like we said below, or said on the previous page, would be 3 favorable outcomes out of the 6 total outcomes, or 1/2, 0.5, 50%. Okay, so got it. 1, our solar system's 8 planets in order of least to greatest distance from the sun are Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. What is the theoretical probability that you will randomly select a planet whose distance from the sun is greater than Earth's? Little side note, I like how they include the word randomly here. That's telling you that this is going to be a fair probability that we can trust. Nice connection to the first part of the chapter. Anyways, so you might have a little bit of a shorter way to write this, but we want to make sure we put enough inside the parentheses here so that our audience knows what we're talking about. Since this question only asks for one probability, I wouldn't be picky. You wouldn't have to have this. But any problem that asks for multiple probabilities, you'll need to label using this notation. Since this just asks for one probability, you could have gone straight to the answer. You could either write it as 5/8 or 62.5%, or you could have left it as 0.625, but again, that just doesn't look as nice sometimes, especially with my students. They tend to use one of these two notations. And the reason why we got 5 favorable outcomes is we're not including Earth, but we're counting everything furthest. So 1, 2, 3, 4, 5. Okay, so that's a little recap of theoretical probability. Complement. This is the vocabulary word I can't remember if we spent time on last year or not. If we did, it was more of an extension. The complement of an event consists of all outcomes in the sample space that are not in the event. Okay, so before I go any further, in Alg1, we wanted the probability of the planet whose distance is greater than Earth's is 5/8. If we want the complement of the event, then we would look at all of the planets whose distance is less than or equals Earth. So it's whatever we don't include. So instead of 5/8, it'd be the remaining 3/8. Okay, so that is why I put this little piece of information here. The sum of probabilities of an event and its complement is 1 or 100%. So the probability of the event plus the probability of not the event is 1. And that's your complement, the probability of not the event. Or you might see it as the probability of not the event is 100% minus the probability of the event. So this is a real fancy way to write it, but basically it's just what's left. So here, problem 2 and got it 2. In a taste test, 50 participants are randomly given a beverage to sample. There are 20 samples of drink A, 10 samples of drink B, 10 of drink C, and 10 of drink D. What is the probability of not getting drink A? So there's a couple ways you could approach it. We know the probability of getting drink A is 20 out of the 50, or we can reduce it 2/5. So the probability of not drink A would be 1 minus 2/5, or the remaining 3/5, or 60% if you prefer percentages. Okay, if you wanted to approach it a different way, you could have said, well, if I add drink B, drink C, and drink D up, I would get the total. And that's true as well. It's just a tiny bit more work. So by approaching it with the complement instead, which would be this piece here, we get to the answer just a little bit faster, in my opinion. But you can use either method. So if we take a look at got it 2. Suppose a taste test is repeated with the same number of samples of drink A, but more samples of the other drinks. So we still have 20 samples of drink A, but we increased all of the other ones. What happens to this complement? What happens to the probability that you don't choose drink A? Well, the probability would decrease because if you think about your fraction, your numerator is staying the same. Your numerator is staying 20, but you're increasing all your other drinks, which is going to increase your total. So your total, or your denominator, your total outcomes is getting bigger. So that means your probability of not getting drink A would increase. So if I back up to this example here, the probability of drink A is 2/5. Or we can even use this to make it even simpler, 20/50. If we increase the other drinks, this number down here gets bigger. So it could be 20/60 or 20/80. So we're going to make this fraction get much, much smaller, which would make the complement have to get bigger and bigger. So that's why the complement would increase. Okay? Or if you addressed it the other way, you could have added and thought of it as all of drink B plus drink C plus drink D. You would still get the same idea. The complement would increase. Okay, so here we're skipping odds. I would have mentioned this last year as well. The only thing I want to say about odds is often students misunderstand them or misspeak them as probability. So if you ever say the odds of not getting drink A is 3/5. That's actually inaccurate. That is probability. Odds is when you say favorable outcomes over unfavorable outcomes. So your denominator is not the total, your denominator would be what's left over. So you don't want to get those mixed up. Well, we're not going to spend any time on odds. The final definition, but the second type of probability is experimental. So you find it the same way. You look at favorable outcomes out of total outcomes, but more specifically, you're looking at the number of times the event occurs, which would be favorable, out of the number of times the experiment is conducted, which would be total. So this could be where you're actually rolling a number cube 100 times. You might not get the perfect, like we set up here, 50%, but you should get very close to it. The larger your sample space is, the more accurate you will be. So that's how experimental probability works. It's actually based on data rather than theory. So got it 4. After receiving complaints, a skateboard manufacturer inspects 2,500 skateboards at random. There's that random again. There are 2,450 skateboards with no defects. What is the probability that a skateboard selected at random has no defects? Well, we would use, this is based off data. So even though we're finding it the same way as theoretical probability, excuse me, it's technically considered experimental. So we divide, which means we want to either simplify the fraction or write it as a percent. Okay, and this note leads us into our final example. You can use probability, whether it's theoretical or experimental, to make predictions. So this is our last example. A manufacturer inspects 700 light bulbs and finds that 692 of them work. There are about 35,400 light bulbs in the warehouse. Based off of our data of what he did inspect, we want to find about how many of the light bulbs in the warehouse are likely to work. So let's start by finding, we can either consider probability or proportion here. So I wrote them both ways. So the probability that they work, set up your fraction, reduce it. That's a really good percentage here. We don't want to round to the end. Or if we set it up as a proportion relationship. Okay, so if 173 out of the 175, which is my reduced fraction, is our probability, then what number out of the 35,400? Or we would just take our fraction and multiply this to the other side to get our answer. You could have used 692 over 700 instead here. In fact, I imagine most of you probably would, just because you have your calculator anyway, so this might seem like an extra step. But you're setting up your proportion of out of how many are favorable out of total inspected, then we predict how many out of the total in the warehouse. Cross multiplication or isolate the variable. And this is number of light bulbs, so even though we get a decimal answer here, we don't quite have another full light bulb, so we'd round down. About 34,995 light bulbs. Should work. Okay, again, this one would be considered experimental because it's based off data, not based off of theory. Theoretical probability would be one flip of a coin, one spin of a spinner. We did a lot of that last year. So, but that wraps up our lesson. So hopefully a lot of that was review. If any of it was not review or it just didn't quite click, make sure you email me with additional questions. Otherwise, this is it. I'll see you later.